27.1 Electromotive Force. In this session, we will explore the fundamental concepts of direct current circuits. We begin by defining the sources of electromotive force, often abbreviated as EMF, and examining how a battery's internal resistance affects its terminal voltage. We will then analyze how power is distributed and dissipated within these circuits. Finally, we will discuss the maximum power transfer theorem, which dictates the conditions under which a battery delivers the most power to an external load. Direct current, or DC, refers to an electric current that remains constant in both magnitude and direction over time. To maintain this flow, we use a source of energy, like a battery. You can visualize a battery as a charge pump that performs work on charge carriers, moving them uphill from a point of lower electrical potential to a point of higher potential. The electromotive force, denoted by the Greek letter epsilon, represents the maximum possible potential difference or voltage that the source can provide between its terminals when no current is flowing. It is important to clarify that the term electromotive force is a historical misnomer. It is not actually a force measured in newtons, but a potential difference measured in volts. In an ideal world, a battery would have zero internal resistance, meaning its terminal voltage would always equal its EMF. However, real batteries are made of physical matter that naturally resists the flow of charge. This is known as internal resistance, denoted by A lowercase r. Because of this internal resistance, the actual voltage available at the battery's terminals, called the terminal voltage, will decrease as the current increases. To analyze a real-world circuit, we model a battery as an ideal source of EMF in series with its internal resistance, R. This relationship is captured in the circuit diagram shown here, where the dashed line represents the physical boundary of the battery. As a current, I, flows through the battery, there is a potential drop across the internal resistance equal to the product of the current and that resistance. Consequently, the terminal voltage, delta V, is calculated as the EMF minus this internal drop, or epsilon minus I times R. If the circuit is open and the current is zero, the terminal voltage simply equals the EMF. By looking at the graphical representation of potential changes, we can trace the energy journey of a charge moving clockwise through the circuit. Starting at point A, the potential increases sharply as it passes through the ideal EMF source to point B. As the charge moves from C to D through the internal resistance, the potential drops by an amount equal to I times R. Finally, as the charge moves through the external load resistor, R, from point E to F, the potential drops again by an amount I times R, returning to its original level. This visualization helps us track exactly where energy is being gained and lost. In a simple series circuit, the terminal voltage provided by the battery must be entirely consumed by the external load resistance, R. This gives us the equation EMF equals I times R plus I times R. By rearranging this formula to solve for the current, I, we find that the current is equal to the EMF divided by the total resistance of the circuit, which is the sum of the external load resistance and the internal resistance. This demonstrates that the current is not just a property of the battery itself, but depends on the entire circuit. If the load resistance is much larger than the internal resistance, we can often simplify our calculations by neglecting R. When we look at the power distribution in a DC circuit, we multiply our voltage equation by the current. This shows that the total power output associated with the EMF is split into two parts: the power delivered to the external load resistance, calculated as I squared times R, and the power wasted as heat within the internal resistance, calculated as I squared times R. From an engineering perspective, if you want a device like a motor or a light bulb to operate efficiently, You want the highest percentage of power possible to reach the load. This is why high-quality batteries are designed to have the lowest internal resistance possible. Let us address two common misconceptions regarding batteries. First, a battery does not actually supply the electrons that flow through a circuit. Those electrons are already present in the atoms of the wires. Instead, the battery creates an electric field that exerts a force on those existing electrons, causing them to move. Second, a battery is not a source of constant current or constant terminal voltage. While the EMF remains constant, the actual current and the voltage measured at the terminals will fluctuate depending on the resistance of the load you connect to it. To see these concepts in action, consider a battery with an EMF of 12 volts and an internal resistance of 0.05 ohms connected to a 3 ohm load. By dividing the 12 volts by the total resistance of 3.05 ohms, we find a current of 3.93 amps. The terminal voltage is then 12 volts minus the 0.2 volt drop across the internal resistance, resulting in 11.8 volts. In terms of power, 46.3 watts are successfully delivered to the load, while only about 0.77 watts are lost internally. In this fresh state, the battery is very efficient, delivering over 98% of its total power to the external device. However, as a battery ages, its internal resistance increases due to chemical changes. If the internal resistance in our previous example rose to 2 ohms, the total resistance would jump to 5 ohms. This significantly reduces the current to 2.4 amps. The terminal voltage would drop sharply to 7.2 volts, and the power delivered to the load would plummet from 46.3 watts down to just 17.3 watts. At this stage, nearly 40% of the battery's total energy is being wasted as internal heat. This illustrates why an old battery may still show its rated voltage on a voltmeter when disconnected, but fail to power a device once a load is applied. The maximum power transfer theorem helps us determine when a battery is most effective at delivering power. By expressing power as a function of the load resistance R, and using calculus to find the peak of that function, we discover a specific rule. By differentiating the power equation with respect to R and setting it to 0, we find that the maximum power is delivered to the load when the load resistance exactly matches the internal resistance of the source. As shown in the graph, if the load resistance is either much higher or much lower than the internal resistance, the power delivered to the device will be less than this peak value. To summarize the key takeaways, the EMF is the maximum theoretical voltage a source can provide. Real-world sources always have an internal resistance, R, which means the terminal voltage is always lower than the EMF when a current is flowing. The current in the circuit is determined by dividing the EMF by the sum of the load and internal resistances. Power is always split between the external load and the internal components of the battery. Finally, for applications where maximizing power delivery is the goal, we must match the load resistance to the internal resistance. To conclude, consider these two review questions to test your understanding. First, based on the relationship between terminal voltage and internal resistance, can you explain exactly why the voltage at the terminals drops as you draw more current? Second, if you were tasked with designing a high-power heating system, what specific relationship should you aim for between the resistance of the heating element and the internal resistance of your power source to ensure the maximum possible energy transfer? Reflecting on these will help solidify the concepts of EMF and circuit efficiency.